I teach at the Interactive Telecommunications Program at NYU, and that's a 2-year grad program. And what I do is I teach people to make things that react to their behavior in ways they haven't thought of before. To give you a little background, ITP started about 1979. It was started by this woman, Red Burns, and she started it when she first saw this camera, the Portapack camera. The Portapack was, at the time, a relatively lightweight, relatively affordable video camera. And Red saw it as something that was going to change people's relationship to media. She saw that instead of just passively consuming media, they were going to start being able to produce and participate in the production of media. And so she was inspired to start the Alternate Media Center at NYU, which then later became ITP. There's 2 reasons that I stay at ITP. The first one is that we try to make it a very convivial place, a place we try to get people who like to work with other people, because we find that you generate better ideas when you share them with people. And the second reason is because we explore ideas there through making things. We make installations, we make devices, we make applications, and we try them on each other and on the general public as a way of sharing these ideas and seeing them mutate. Red's driving principle that when you take people and give them access to technology and give them an understanding of technology, that they will then be empowered to become active participants in the change that technology brings about, is still our driving principle for the entire school, or for the entire program, excuse me. We've seen this change happen over and over again through many different shifts of media and technology, and continues still today. I run the physical computing program at ITP, and what I mean by physical computing is that I introduce people to thinking about computation from the point of view of what people physically do. The first question we ask when we start to build physical computing applications is, what's the person going to do? What actions are they going to take? For example, this guy is building a flight simulator. And unlike a typical flight simulator where you might start with the game controller and have somebody doing this kind of thing, he said, well, what does a person do that indicates flying? Well, they flap their wings. So he made a series of sensors that lets him flap his wings and drive the flight controller. Or as another example, this is Steven. Steven has muscular dystrophy, and he loves playing Major League Baseball on his PS3, or he did until his MD really slowed him down quite a bit. His occupational therapist, Holly, worked with a team of other ITP students. She was a student there at the time. And they built a controller for Stephen that allowed him to take advantage of his own abilities rather than having to be stuck in the box of other people's abilities. So this is, for me, one of the best things about physical computing, when it can really expand people's abilities by working with what they can do rather than against what they can't. To do this, we have to teach people about electronics, we have to teach them computer programming, we have to teach them to think about action, all of these things, because we don't assume any discipline when they come in the door. And we introduce them to this. This is a computer, this is a microcontroller, and you probably have 4 or 5 on your body right now. They're usually only a couple bucks in price at most. They have no physical interface, and in order to give them a physical interface, you build something on them. You add motors, you add speakers, you add lights, you add sensors, you add switches. You can build anything you want with these. Now, traditionally, these microcontrollers have been the province of trained electrical engineers rather than dilettantes like me and my colleagues. So the first few years we taught, it was rather difficult to get across to people how to use these, just because you had to understand so much about the background before you could use them. But about 7 years ago, I got involved with a group called Arduino that were making a microcontroller platform for people who didn't understand the technology, for people who were coming at it from beginners. And I'm a co-founder of the company now. We've been going, as I say, for about 7 years. We've got distributors in 40 or 50 countries, and it's starting to actually sell pretty well. Arduino is open source hardware, and what that means is that when we sell the boards on our site, we also put the plans up for how to make the board on our site, and we put up the code for the software for how to use it on our site. So in addition to making things with Arduino, you can also make your own version of it. And there are dozens of companies that are making their own versions of it, starting with our plans and then making variations on it. And that's one of the things we're really happy to see happen. There are actually 4 parts to the Arduino system. The first is this hardware board, which just plugs into your computer straight away, so we took away a lot of the hardware difficulty of getting started with microcontrollers. The second part is the software system, and the software system, again, we tried to make it fairly simple, something where people could understand it right away rather than having to deal with all the bells and whistles. The third part is the hands-on examples. We wrote a lot of very basic examples to get you started so you could understand what you could do with this thing and didn't have to spend a lot of time understanding that. And the fourth part, and I think the most important part, is the community. There's all kinds of really great people using it, and they're borrowing from each other, they're borrowing from our original plans, they're making new things, they're putting that back into the community to expand what it can be done with. So I want to talk about that a little more in depth because some of the things these people are making is absolutely amazing to me. Because we aimed at artists and designers to begin with, the first thing we see a lot of is really great art and design projects, like this guitar controller from Paul Rothman. Paul's a musician, and after a year at ITP, he built that guitar. We also see things like this color field sculpture from Matthew Richard. Matthew was a painter before he came, and he was really interested in using light and mechanics to make color field paintings, so he made this one. Sometimes we see things that you don't exactly know why you built them, but they're fun. If you can imagine, Tom Gerhardt built a tub of mud, and this tub of mud was, about this big in front of you, and he wanted to use mud as a way to manipulate the mouse and the keyboard. So he had this whole tub of mud, and you just slide your hands through the mud. It was wonderfully visceral. So in order to go on to the next slide, you would just get, and you'd be on to the next slide. But the really interesting things for me right now are the tools that users are making with this stuff. This is an example. This is the laser saw. It's a laser cutter, and basically what you've got is a microcontroller and 2 motors and a laser. And the microcontroller takes a 2D file, like an Illustrator file or something like that. It translates that file into a series of movements for the laser so that the laser is guided in cutting some material beneath it. Now, laser cutters aren't new, but this one's a little different in that it is also open source hardware. So the folks who make this, 2 of my former students, in fact, they put the plans online. So you can take their plans and make your own version of it as well. You can also buy a kit from them to build your own. And this is another place where the laser saw is a little different than other laser cutters. Typically, a laser cutter is going to run you around $8,000 to $10,000 at the low end to buy one. You can buy this kit for $512. So that's just one of many tools that's getting made. Here's another one. This is the replicator, and this is a 3D printer. It's made by a company in Brooklyn called MakerBot. And it's very much like the laser cutter, except it's got 3 axes of motors instead of 2. And instead of a laser, it's got a heated head that drips plastic and creates these forms like the chessboard here by building them up rather than cutting away. We're seeing dozens of these kind of tools getting made by users now. We're seeing 3D mills, we're seeing 3D routers, we're seeing one of my favorites, the Candy Fab, which is a printer for candy, prints out like little marzipan things. All kinds of tools that people are making with these microcontrollers. Now, just to step back a little bit, if you remember the desktop printing revolution, then you remember clip art. Clip art is actually what told us what we could do with laser printers, with graphic programs, and so forth. And every program came with some clip art, and you could use it in your work. And we all put out the cliched letterhead that had, the little cat on the top or something like that. But we learned through that how to use desktop printing. Here is clip art for the 3D fabrication world. Thingiverse is a website that allows you to upload your own plans for things you've built, to download other people's plans, to modify and put them back up, and it encourages the community to do just that. Thingiverse is not unique. There's a whole bunch of other sites that are doing this. They're basically giving you a place to upload plans, and many of them will also actually cut or build those plans for you because if they're assuming you don't have the tools yourself. There's even a few of them that have marketplaces where you can upload plans. They will then produce the actual materials, make kits, sell those kits, and share the profits with you. And this isn't just happening in online space. It's happening in real space quite a bit too. This is NYC Resistor. It's a makerspace here in town. And it's a place where people come together and make stuff on their own free time just for fun. It's a very convivial place, people learning from each other how to do this stuff all the time as well. And it's actually the place where MakerBot began. They started here as the guys who started the hackerspace, and they said, hey, we can start a company as well. Now, Eric Van Hippel at MIT talks a lot about user-driven innovation. And these hackerspaces, and there are 400 or 500 of them around the world at this point, are really where it's happening in terms of that. These people are starting these kind of companies like this, and they're the kind of thing that are going to take schools and established companies, and they're going to drive us out of business. So we need to be paying attention to these. And it's not just in mechanics or electronics either. You look at GenSpace here in New York City, you look at BioCurious in San Francisco. These are biohacker spaces. They're doing biotechnology in the same way, getting beginners in the room after work, playing around with biology. It's really quite amazing to see. Now, in order to think about the change that's going on here, we have to think about a change in intellectual property. So this is 3 different views of Nikon's intellectual property. These are instantiations of the flow of Nikon's intellectual property. But in this model, innovation only goes outward from Nikon to its customers. In another model, taking the Thingiverse model, users download plans from the companies that they buy things from, or they copy them and they scan them. They make their own versions of them. They improve upon them. They add new things that make their cameras more valuable. These people are still buying cameras from the big manufacturers, but they're making more value for the things they buy by adding on to them, and they don't have to wait for the manufacturers to do that. I want to see a place where there's flow between these 2 different models. Now, some people think that this is actually going to be bad for big manufacturers. They say we're going to see more clones, you're going to see more people getting ripped off, but I don't think that's necessarily true. For one thing, digital fabrication is not very fast. It's not good for making 1 million units, but it's great for making 2 or 3 customized versions of a plan that's already out there. So companies could start to think, instead of having stock rooms full of spare parts, you've got an online repository of the plans and a fab printer. Somebody has a broken device, they go to your center, gets printed out, it's fixed. But it's not quite all sunshine and roses here. There is a lot of danger, possibly, and there's a lot of threat. We saw what happened recently with SOPA and PIPA, where there's a lot of push to shut down large parts of the net in order to protect intellectual property, supposedly. Those threats are still going to happen, and we're still going to see scare threats. And this is an example. This is what's called an ATM skimmer. And it attaches on the faceplate of an ATM, and you stick your card in, and it copies your card info. And when you finish your transaction, you never know that somebody copied your card info, but there it is. In 2010, a user of the site iMaterialize, which I showed you earlier, uploaded plans for making a skimmer to iMaterialize. Now, the company that made that made iMaterialize, immediately pulled it down and refused to produce the device. But the politics of companies that are producing these things is varied, and some of them are not going to agree that they should be taking that kind of thing down. And we're going to see more of these kind of threats. We need to be prepared for that, and we also need to be prepared for the legislation. We saw with SOPA PIPA that uninformed legislators will use a chainsaw when they should be using a scalpel. And so that means that policy is another place we need to step from being passive consumers into being active participants in the process. We need to defend what's going on in this world with our own values and put that into politics. You see some sites that will try and prevent certain things, and a lot of us will put our values locally into our sites. This is from Thingiverse, and you can see they don't allow the upload of weapons, but in fact, people still upload weapons to Thingiverse. And for every site that says, I won't have weapons, there's a site dedicated specifically to it, like cncguns.com, where you can do nothing but learn how to make a gun. So, again, there are dangers out there, but these dangers are being managed within those local communities. And those local communities now need to step forward and say, our limits and our possibilities, we're going to put forward into larger public policy. So we all need to be participating in public policy. And here's one way we can do it. This is Peer-to-Patent. Peer-to-Patent is a site that was put together by New York Law School, and it was done for the Patent Office. The Patent Office has a problem where there are far too many patents to get processed, so they often get glossed over. Peer-to-Patent, anybody can sign up. You can then go on and you can review current patent applications with your expertise, whatever it may be. So if you see missing prior art, you can comment on it. If you see false claims, you can comment on it. And all of that goes into the patent application so that when a reviewer finally sees it, they've got the benefit of perhaps thousands of experts who've had a look at this. This is the kind of participatory policy that I'd like to see happening a little bit more. So I'm going to leave you with one last thought here. The devices that we make and the devices that we use What they do matters less than the relationships that we make through them and how they change our relationships. Being informed about how they're made and being informed about how that policy is made will make our relationships ultimately stronger through it. So I encourage you all, get your hands dirty. Thank you very much.